When acid and base reactions happen, we have four different ways in which they can combine for neutralization reactions. We have the strong acid with strong base, weak acid, strong base, strong acid, weak base, and weak and weak together. So when you are determining what to do in order to find pH, you have to take this into consideration because strong acids, strong bases will completely dissociate and the weaks will not. So you'll have to do some ice charts, some equilibrium expressions for that. So one way to identify what to do based on a problem is to take into account the major species that are present in the reaction. So what dissociates into its ions? What are spectator ions that don't really have any effect, and so you can just take them out of your reaction. And then also, based on the list that we have on in our notes on page 5, is it a strong acid? Is it a strong base? The strong bases are talked about at the top of page 6. So recognizing those things, that is important to see. And then once you determine the major species, that will help you to know how to solve the problem, how to attack the problem. Do you need an ice chart or not? If everything is strong and everything's dissociated, then no, you don't need an ice chart. But if you have something that is a weak acid or base, you do need that ice chart. Okay, and then also something else to consider with neutralization reactions, when we are adding these aqueous solutions together, we actually will dilute the molarity slightly. And so we have to use this, it's called the dilution equation, where the M1 and V1 are the original given information about the solution, and then M2 would be the new molarity after the dilution part of them mixing together has happened, and the volume 2 would be the total volume for the solution, which you would add together the two volumes of your acid and your base, add that together for V2. Okay, so for example, if we have 25 milliliters of 0.5 molar hydrochloric acid react with 25 milliliters of 0.5, that's supposed to be molar, ammonia, NH3. In this case, the mathematics will be the same for either one because the volume and the molarities are equal, but let's just pick the acid this time for the hydrochloric, where we originally know that we have 0.5 molar and we've got 25 milliliters of that. And so we're determining what the new molarity is after it has slightly been diluted when it has been first mixed with the 25 milliliters from the other solution. So for V2, we take the two volume amounts and add them together. So 25 plus 25 is really 50, okay? So then when you solve for M2, you get 0.25 molar. So when you do have neutralization reactions, the volumes will be taken into account, and we have to make some corrections on the molarities in order to then use those corrected molarities in our reaction equations, because since they have been corrected, that will potentially change the final answers, the pHs, or whatever else you're looking for. So yes, there's just a lot of steps involved. Okay, so our first situation is when we have a strong acid with a strong base. They will completely dissociate and they will completely neutralize each other. And when they do that, they produce an ionic salt with water as their final products. So here I have hydrobromic acid reaction with sodium hydroxide to make sodium bromide and water. So the major species for this reaction, we've got, so breaking apart the strong acid, we've got H plus and Br minus, both from the HBr. And then from the NaOH, we've got the sodium ion and the hydroxide ion. And then on the product side, I don't need to include anything from the sodium bromide because it's already still there. Those are the same ions, those spectator ions, we call them, that are still floating around. They're not forming a solid or a liquid. So they're still floating, and then liquid water. So at this, when we remove the spectator ions, then we can get the net ionic equation for this reaction where it's the hydrogen ion plus the hydroxide ion to make water liquid. So whenever it's a strong with a strong, this is just really nice because it will reduce down to this. And the H plus always belongs to anything about the acid. The OH minus belongs to everything about the base when you plug in, okay? So then when we want to find the pH of the resulting solution, once the strong acid and strong bases are mixed together, we have to determine this from the excess reactant. So we will have to do an additional calculation for this. And how we're going to set this up, we need to know it from the excess reactant. So we have to use up the smaller of the two reactants, where just similar to an ice chart, we're going to have like the before line for the concentrations, then RXN stands for reaction. That's how I abbreviate it. And then the after would be when we use up the reactants. Okay, so just for example, like if we have A plus B to make our water or our base, or yeah, let's say water, sorry. Let's say that we've got like 0.1 of A and 0.05 of B. Water doesn't matter because it's not going to have a concentration. So we will be able to tell right away what's the limiting reactant. It's the one that has less, okay? We can just assume that the reaction stops when we run out of the smaller of the two. So we will subtract the smaller of the two values, leaving us with new concentrations, where one of them has completely run out, and then the other one has significantly less after we've run out of that. And so then this amount from the excess reactant will then lead us into how we solve for pH, okay? I should have put H plus and OH minus, sorry. Anyway, so we've got a reaction between 35 milliliters of 0.2 molar HClO3, which is chloric acid, reacting with 15 milliliters of 0.2 molar potassium hydroxide, KOH. So we want to determine the pH of the solution there. Okay, so we should know that this is a strong acid with a strong base. So we know that the ClO3 is going to be a spectator ion. We know that the potassium is going to be a spectator ion, which will automatically get us to our equation of H plus with OH minus to make water. Okay, but when we plug in for the before, we have to take into account the diluted parts of the reaction. So the molarities are slightly different than 0.2 and 0.2. Okay, so to find for the acid molarity, we are going to do that N1V1 equals M2V2 thing. So the acid starts with a 0.2 molar, and we have 35 milliliters of that. So the new volume will be the 35 milliliters plus 15 milliliters from the base, so which is a total of 50. So the new volume for the acid will be 0.14 molar. So I'm going to plug that number in right here. Okay, then we'll do the same thing with the base, and this time they're not going to be the same numbers. So for the base, we have originally 0.2 molar and 15 milliliters of that. And then our total volume is going to be the same, 15 plus 35 or 50. So the new volume or the new molarity of the KOH will be 0.06 molar. And water doesn't matter. Okay, so now when the reaction happens, we're going to use up the limiting reactant. And so it's pretty obvious that the hydroxide, the base, is the limiting reactant here. It's less than the acid. So we are going to subtract from both the 0.06. So then after the reaction takes place, we now have 0.06 0.08. I should be keeping significant figures, I'm sorry. 0.080 molar is going to be the concentration of our hydroxide, or sorry, excuse me, our hydrogen ion. Okay, so then that number, that 0.08, will then lead us to find pH. So we just have to take the negative log of that, and the pH resulting is, I rounded it up to be 1.10 for that. Okay, so this is for a strong acid, a strong base. Pretty simple, not too involved. Yes, we have to do that correction for the molarities, but then that's it. Next situation, when we have a weak acid with a strong base. At this point, the weak acid doesn't completely dissociate. So we cannot just put the H plus into the equation. We have to keep it as the acid, HA. Okay, but since the base is strong, then that does completely dissociate. So we only need to include the hydroxide from that. So the resulting reaction, when you have those two react, will make the conjugate base and water. And so because the weak acid does not completely dissociate, this is going to be equilibrium state. So we have to have our equilibrium arrow in there instead of just a forward facing arrow instead. After determining our new concentrations, then we have to use an ice chart in order to find the pH. We can't just use a number right away. We have to use that ice chart. We will still do the before reaction after as well to see and use up the excess reactant. So we want to know the resulting pH of the solution when 20 milliliters of 0.5 molar acetic acid reacts with 25 milliliters of 0.2 molar sodium hydroxide. Now we've been given the Ka value for the acid, which will be used when we get to the ice chart and not before. Okay, so we first have to, let's figure out those new concentrations. Okay, so I'm going to just, instead of acetic acid, instead of this big thing, I'm just going to use HA to signify acetic acid. Let's write. For that one, we start out with 0.5 molar, and we've got 20 milliliters. And our new volume will be the 20 milliliters plus 25 from sodium hydroxide. So that's a total of 45. So then the acid's new molarity is 0.22. And so then for our base, the sodium hydroxide, same process, we've got 0.2 molar times the 25 milliliters of that is equal to our new molarity times 45 for the volume, for the new volume. And I got that the base's new molarity is 0.11 molar. Okay, so using that equation that's right there at the top of page 14, we have our acid plus the hydroxide, which is the important part from the base. We don't need the spectator ion. That will break down, that will turn into the conjugate base, the acetate ion, and water. Okay, so water still doesn't matter. Before the reaction takes place, we have our new concentrations where the acid is 0.22 and the hydroxide is 0.11. But this time we have the conjugate base in there. We have the A minus. That is not a liquid, that is not a solid. So we need to account for that with our calculation. So we have to say that we have initially 0 there. So now when the reaction takes place, this is going to be similar to how we do ice charts, where we do want to subtract away the limiting reactant, but then we need to add that same amount to the product side, to that conjugate base. So then after the reaction takes place, our new concentration, we have 0.11 left for the acetic acid, 0 left for the base, the hydroxide, but we've got 0.11 molar for the conjugate acid as well. Okay, so now since we have some of the acetic acid left over, that tells me that when I go to find pH now, I can set this up with the acid equilibrium like we did in example 7. Sorry, that's association. Like example 5, okay, where we have our weak acid plus water makes hydronium and the conjugate base. So now we're getting into the ice chart portion, okay? So for this equation, we have our acid, and it's gonna dissociate with water, and it will form the hydronium ion and the conjugate base. So once the reaction's done, now we have to use this dissociation method so that we can figure out how much hydronium we have to then figure out the pH value, okay? So after the reaction is done, initially we've got 0.11 molar for the acid. Water is not important. We don't have any hydronium, but we also have 0.11 molar of the conjugate base from that before reaction after that we just did, okay? And so then our change, this is acid, so I'm going to use an A for that. So at equilibrium, the hydronium will just be A, the conjugate base will be 0.11 plus A, and the acid will be 0.11 minus A, okay? So now we can plug in to an equilibrium expression and solve for A. And remember, we make assumptions here. For acids and bases, the change will be so tiny that we do not have to add or subtract anything. So our Ka value given is 1.8 times 10 to the negative 5 is equal to, the hydronium is A, and then we have 0.11 plus A for the conjugate base all over 0.11 minus A. Well, remember, we're making the assumption so we can get rid of our plus and minus A. So this turns into 1.8 times 10 to the negative 5 is equal to A times 0.11 over 0.11. So the 0.11s cancel out. And so A value, which is our hydronium ion concentration, is our Ka value. 1.8 times 10 to the negative 5 molar. Okay, so then now, last but not least, we wanted pH here. This is the whole point of this whole problem, is to find pH. So all we have to do is take the negative log of that number, and that will give us pH. And I got 4.74 for that. So this is an example of when you combine a weak acid with a strong base, and what has been left over after the reaction's over is acid. So then you can use the equilibrium expression for the dissociation of the weak acid to then solve for the pH value. Now, when we have this situation, we create what's called a buffered solution. A buffered solution is one that will resist change in pH when either hydroxide ions or protons are added. And this is because it contains a solution of a weak acid or a base and its salt or its conjugate base. Okay, so we can make a buffer solution from a weak acid and its conjugate base, or a weak base and its conjugate acid. We're going to talk a lot more about buffers in detail in 8.8. But for now, you just need to know that it resists change to pH. So that means that we won't have jumping around pH values. It's going to stay pretty consistent and be very, very tiny changes, if any at all. So if the weak acid is added in excess to this, in this situation, a weak acid with a strong base, then we can result in a buffered solution where we do not have a strong change in jump of the pH value. But if the strong base is added in excess, then the pH can be calculated from its moles of excess hydroxide and the total volume of the solution given. If they're equal molar, then the solution will be slightly basic, and then we can determine the pH using the basic equilibrium that we learned about the other day. Okay, so we'll talk more about buffers in 8.8. Now let's talk about when you have a strong acid combined with a weak base. So when a strong acid and a weak base combine, the reaction is described by this net ionic equation, where B stands for base. It reacts with the hydronium ion because that hydronium ion is present since the strong acid completely dissociates. And that will create an equilibrium situation where we recreate this conjugate acid, the Hb+, and water. So with this process, we will do the same thing that we just did, but when it gets time to be an ice chart, it depends. Are you going to use the acid K or the base K? It all depends on what is the leftovers after the reaction happens, okay? So in this example, I chose one where it happens to be a base, but it's not always like that. You have to be careful and see where do your numbers lie, okay? So we have 15 milliliters of 0.1 molar hydrochloric acid mixed with 15 milliliters of 0.2 molar ammonia, which is NH3, Kb given. Determine the pH of the resulting solution. First thing you got to do, let's dilute these things. Okay, so for the acid, we start out with a 0.1 molar solution times 15 milliliters. And the new volume will be 15 plus 15. So my new volume for the acid is 0.05 molar. Okay, and then for the ammonia, the NH3, we've got 0.2 molar, 15 milliliters originally. Total volume is filled with 30. So the new molarity here is 0.1 molar. Okay, so now let's figure out what happens for the reaction. So writing down the equation for the reaction, we've got our weak base, ammonia, NH3, reacts with the water, reacts with the acid, which is strong. So we're gonna write down the hydronium ion for that because it's completely dissociated. And so the hydronium ion will donate its proton, because that's acting as the acid, to the NH3 to make this NH4 plus 1 called ammonium, and then the resulting leftover will be water. Okay, so before the reaction takes place, we plug in our concentrations that have been adjusted. We've got 0.1 for the ammonia, we've got 0.05 for the hydronium, and just like it was in the last example, we have 0 for the ammonium. It's not a liquid, it's not a gas, it's not a solid, so we have to include it. But water doesn't get included. So now during the reaction, we're using up our limiting reactant, which happens to be hydronium this time. So subtract away the hydronium amount and add it on the product side. So then after the reaction takes place, you'll have 0.05 molar of the ammonia, nothing of the hydronium, and then 0.05 for the conjugate acid. Okay, so since we have the base left over, we are going to use the conjugate base, the weak base equilibrium expression to then find what the hydroxide ion is. We're not going to use the acid because there's no hydronium left, okay? We have to use the base because there's no hydronium left. So I need to erase this. So for that base equation, and I'm getting this from the near the top of page 11. The base is our NH3. React with water to result in the NH4 plus 1, the conjugate acid, and hydroxide. So when we have leftover base in the water, this is how we're going to be able to determine the pH. The base will help contribute hydroxide ions. Okay, so then initially, we're going to use what we just figured out from our before reaction after, and we've got 0.05 for the ammonia, and we do need to include that 0.05 for the NH4, and hydroxide is 0, because hydroxide is what we're trying to find here. So our change, putting B for bases, so at equilibrium, we got 0.05 minus B, 0.05 plus B, and B. Okay, so to save some time, I'm going to go ahead and just set up my equilibrium expression, taking away my assumptions without having to write all that down. So the KB is given 1.8 times 10 to the negative 5 equals, then I've got the 0.05 plus B, I'm taking off the plus B, so it's just 0.05 times B for the hydroxide over, I'm going to take off the minus B, so just over 0.05. So this case, again, we get 1.8 times 10 to the negative 5 is equal to B. Now, this molarity is the hydroxide concentration. Okay, so if we take a negative log of this, we need to do that, but that's not going to be the answer. Taking the negative log of this answer will give us the POH, not the pH, which is what we need. Okay, it's going to get us there though. It'll help us. So the POH, when we take the negative log, is 4.74. And then to find just the pH, now we just subtract that from 14. Supposed to be subtract. And that gives us 9.26. Okay, so I got the B's from that other teacher, and she uses those so that you remember that it's going to be a two-step process to get to the pH at the very end of the problem, not just one step, like it was in example 9. I know this is a lot of work, but it's working our way through to get what these acids and bases are supposed to tell us. Similar to the weak acid, strong base scenario, a buffered solution can be formed with the strong acid, weak base situation. If the weak base is in excess, then we can have this buffered solution. If the strong acid is in excess, then the pH can be found from the moles of the excess hydronium and the total volume. So that means that we would just have to use the leftovers. If they're equal molar, then it'll be slightly acidic, and we would have to use the following equilibrium expression to then be able to determine the pH. So a buffered solution can happen. And last but not least, the weak acid, weak base situation. With this one, since both of them don't break apart, the equilibrium expression doesn't actually include any water, hydroniums, or hydroxides. So you would use this equation here, where HA is the weak acid and B is the weak base, to then do the before reaction after to figure out what has been used up and what's left over. And then based on which reactant was limiting, then you would choose, do I use the Ka value, or do I use the Kb value? Do I use the acid dissociation, or do I use the base dissociation to then determine the pH value? So that would just be the equation you would use to get to the end there.